Hello everyone, in this video we're gonna discuss about the programming code that has been created and used to understand the data to build the neural network for research project. Here we go. We are going to show the autoencoder architecture with the best activation function and discuss about the result by plotting a epoch versus loss graph to show the results. But before we build the network, first we get familiar with the data that we chosen for the study. As I mentioned in the report, we choose a weighted image detection task. So for that, we choose a weighted dataset. So to do the EDA, we first import some useful libraries. We choose Panda for the reading of data. We for transform the data into array. We use NumPy library. We use Matplotlib to build the graphs. Keras library are used to build the network, whereas sklearn libraries are used for the data augmentation task. Now, to understand the data, let's just import the data into a variable name as data. After that, to understand the data and read the data, with the help of Panda, we define a data frame called dftrain and try to print the header file of the data frame. So from the output, you can see the image ID, the width of the image, height of the image, and the bounding boxes, and also the sources from where the image has been collected. After that, we print the shape of the training data frame, also the sample data frame. So here you can see the shape of the data frame. After that, we try to print the unique value of the data frame. After that, we're gonna print the size of the images that we have. So the output shows we have 1024 into 1024 width and height of the images. Now we're gonna plot the total number of images that are present in the train and the test, and the data that have no grains in it. So as you can see, these are the number of images that we have. After that, we try to print some images from the training data. So here are 8 images from the training data. I plot some more images for the references. After that, we define the bounding box into X and Y and try to locate the bounding box in the image. So from the output, you can see the bounding boxes are now defined into X and Y coordinate, and the width and height are defined as the pixel locations of the bounding box, which helps in the early next steps to print the bounding box of the weighthead to locate the weighthead on the images. In the next step, we're gonna define a function to show the boxes on the images. So after defining the function, some images with the weight head are gonna show with the yellow bounding box. As you can see in the output, there are some images highlighted with the yellow bounding boxes, which shows the images, which shows the location of the weights in the images. Some more images are gonna print. After that, we try to print the images that don't have any kind of head. So before that, we're gonna try to print the number of images that we have that don't contain any head. There are 77 images that don't contain any kind of head. So before doing that, so we try to print some of the images that don't contain any head in it. As you can see, there are 8 images for the references that don't contain any kind of beathead. Now we're gonna build the autoencoder neural network to train the model. So before that, we're gonna try to import some libraries such as Keras, TensorFlow, uh, PIL, and Random. Mm. Now we're gonna define the input size of the images, which is 125, and also we define the batch size, which is 64. With the help of the image generator, we rescale the image and also divide the data into three classes, as you can see in the output. Now we're going to define the convolutional autoencoder model using sequential function. Now as you know, the autoencoder compress the input image to the bottleneck and then try to recreate it. That is why we use a max pooling in the encoder part and upscaling in the decoder part. Also, we find out by trying the different activation function and combination of activation function. The combination of ReLU, pReLU, eReLU are performed the best when we apply it from the first layer to the last layer respectively, as shown in the codes. The encoder and the decoder should be the mirror image of it. That's why we define the model in that way. Now, in the summary, you can see. Now, in the summary, you can see the network first compressed the image from the 128 to 16 and then try to reconstruct it to the 16 to 128. Also, by using the combination of activation function, the learning parameter also increases, so which helps to perform the network very efficiently. We use the Adam optimizer and mean square error to check the loss of each epoch. Now let's train the model for 25 epoch and see the results. We are going to train the model using the model fit function. Now, as you can see, the training started.